Thank you. It's wonderful to be here again. I would like to tell you some things about stuff that's happening in quantum systems and physics, and in particular topological quantum matter, which is what we got the Nobel Prize for. So the key thing in quantum mechanics these days is the property of entanglement. And we're going to talk about entanglement in topological matter and the dream of topologically protected quantum computer, which is a big goal of people in the field, but hasn't been achieved yet. But we'll see what happens. Okay. So the basic message here is that as we understand quantum mechanics better, there's lots of big developments in material science and producing interesting new materials with quantum properties, and these, I think, will be the basis of new technologies. But these have arisen through a whole series of rather surprise developments. One of the exciting things in condensed matter is the frequency at which new surprises have come about, the latest being the moire flat bands, which we'll talk about later. So quantum mechanics goes back, it's now 100 years. It's the 100th anniversary of quantum mechanics. It's going to happen this year. And the laws of quantum mechanics were settled a long time ago. The basic laws were established by these gentlemen. And so far, all tests of these laws show they're correct. But just because we know the laws doesn't mean we know what quantum mechanics is capable of doing. And again, this goes back to starting around 1980. I'm going to talk about some of the new insights into quantum mechanics that emerged in condensed matter with topological materials. But earlier than that, the thinking about quantum information theory started with Feynman's ideas when he started thinking about what a computer would be like once I got it down to the sizes of atomic sizes. And what's been happening now is that this emphasis on entanglement, which was really not part of practical physics when I started studying it, was more of a philosophical issue, has now emerged as a practical issue, and it's believed to be the foundations of the so-called second quantum revolution that people often talk about. Okay, so just quickly, classical information is just a binary switch which can be on and off, but quantum information is represented by a two-level quantum system or a spin, which is a qubit, and the state of the qubit is representable by a point on the surface of a sphere, the Bloch sphere, and you can measure it along any axis to get 0 or 1 along some axis. So there's obviously a lot more information storage potential in the qubit than there is in the original classical switch or bit. So the central theme in this new approaches to quantum physics is the property of entanglement. And entanglement is only going to be significant for our purposes when it's over distances which are large compared to atomic sizes. And this is actually now really recognized as a central property of quantum mechanics, as pointed out by Einstein. Originally, when I studied quantum mechanics, the Heisenberg uncertainty principle was being viewed as the kind of central part of quantum mechanics. Well, now I think entanglement is, and it's really viewed now as a fuel which will drive future quantum information processes. So, of course, Einstein, of course, he got his Nobel Prize not for relativity or gravity. He got it for his contribution for the photoelectric effect. So he really got his prize for quantum mechanics. But around by the middle of the 30s, he'd become disenchanted with quantum mechanics. He felt he identified a key property that quantum theory predicted, which he felt was so bizarre it couldn't possibly be true. And he called it, of course, famously spooky action at a distance. But Schrödinger came up with the much more neutral term entanglement, or the German version of that. And what is entanglement? It's a strange property of quantum mechanics that the outcome of a measurement at one place can affect or is correlated with the outcome of a measurement made at the same time at a different place. So basically, if the outcome of a measurement at A influences the outcome of or is correlated with the outcome of a measurement at B, there's an entanglement between A and B. And Einstein vaguely felt this was something like information traveling faster than the speed of light, which it's not, but this was somehow not consistent with relativity type ideas. Okay. So basically, if the distance between A and B is on the atomic scale, there's really nothing special about this because we know we need quantum mechanics to understand the properties of molecules. But what's unexpected and hard to produce is when you have entanglement between places or degrees of freedom which are separated on a much larger scale than atomic. And this is what it's now realized that long-range entanglement is what can be used to store and process quantum information. So one of the fundamental properties of quantum mechanics is the Pauli exclusion principle that says, basically says two electrons can't be in the same state. So in addition to roughly its position, the state of an electron depends on this another internal degree of freedom, the spin, analogous to a spinning top. And of course, the chemical bond is made of two electrons with exactly opposite spins, basically occupying the same region of space in between two ions to bind them together. And the electrons, if one electron has a spin pointing up, the other one will, of course, have a spin pointing in exactly the opposite direction on the Bloch sphere down. And because of the Pauli exclusion principle or the fermions, the quantum state of this is antisymmetric or odd under interchange of electrons. So the quantum wave function is up, down, minus down, up for particles 1 or 2. And that's, of course, the maximally entangled state of the two electrons. So, of course, what Einstein and his collaborators, Podolsky and Rosen, worried about was, suppose I take this chemical bond and manage to stretch it without interfering with this quantum state up, down, minus down, up of the particles. And the question was, when they were a large distance apart, is the real description of this a mixture of up, down, and down, up, which is not determined until you actually measure it, or does it split up? Einstein felt the principle that of local realism that he believed in said that it could not possibly be this equal mixture of up and down and up. He thought something had to determine either one or the other of these two possibilities, and he didn't like the idea that measuring the direction of the spin of this electron would immediately fix the outcome of any measurement of the spin of the other electron along the same axis. And actually, does this picture violate relativity? No, it doesn't, because information can't be transmitted faster than the speed of light, and there's no information transfer between the two agents that measure things on either side. So various kind of teleportation protocols have been made with EPR photons, but they involve picking up a telephone at one end and talking over the telephone to tell the observer at the other end what he'd measured, and then you could do things. But that, of course, the telephone communication has to travel at the speed of light or less. Okay. So this was Einstein's ideas. Were not tested during his lifetime, but various people like David Bohm and then John Bell kind of made a clearer and more precise formulation of the Einstein-Podolsky-Rosen paradox. And eventually the measurements were done, and they were finally rewarded with the Nobel Prize 2 years ago. And basically the results by Clauser and Axbe of the clearer experimental refutation of local reality by John Bell proved quantum mechanics was 100% correct. So no one so far has made their career by betting against quantum mechanics. the predictions are clear and there's no violation of any kind that's been detected. But okay, though you can get entanglement over large distances, but it's very fragile against decoherence. The chemical bond energy gaps make the system rigid, but as you stretch this thing, the gaps which could protect it against interaction with the environment become very weak, and such a thing is going to be decoherent. So in 1980, around, there were actually two condensed matter physicists thought they had a basic understanding of everything. They thought, they developed lots of theories of magnetism, broken symmetry, superconductivity, and of course, when a field seems to think that it knows everything, it's about the time where something's going to come and bring them to their senses. And indeed, two strange things occurred. The most important one, of course, is the discovery of the quantum Hall effect by Klaus von Klitzing. And apparently a very unrelated thing was what I discovered, something to do with magnetism. And these things had no obvious connection at the time, and they were not really obviously anything connected to topology at the time either. But there turned out to be two initial examples of topological quantum matter. And over the last decade, or possibly by now 2 decades, many more kinds of topological quantum matter have been found. So these were the kind of tip of the iceberg. And and in some sense, quantum entanglement is important in the states. So what is topological matter? How does it differ from ordinary matter? It's got some properties, which in some sense are entanglement properties, that can be described by whole numbers, integers like -1, 2, 5, etc. Ordinary matter, we might say ordinary matter might be described by a kind of boring number like 0 or possibly 1. And states of matter which are described by whole numbers can't smoothly change into each other. And so if I have a region where the nature of the condensed matter is classified by -2, and outside that region it's a more normal state classified by 0, there has to be a boundary between the two regions. And the basic property of topological matter is that there's pretty well always something interesting happening on the boundary where this thing changes. And the basic point is that topological properties of materials can't change continuously. And that has some implications. It means that a topological property is robust against, for example, small amounts of dirt in a material. It's quite a contrast to the usual kind of material properties, such as in silicon wafers when we're building our chips, which require ultra-clean systems. And this thing, of course, this suit is not to protect the worker from the noxious chemicals involved in producing gallium arsenide or whatever he's looking at, probably silicon. But it's, of course, to protect the chip from any bits of spit or hair or something that come off the worker. So anyway, in recent years, it's been realized that quantum condensed matter can exhibit sort of unexpected properties which are associated with quantum entanglement over longer ranges. And if I think about what that means, a trivially entangled system is one where basically if I cut it in half, the description of the full system is almost just a direct product of the wave function over here and the state over here. A little bit of entanglement at the boundary, but basically if I do a measurement of something far away from the boundary here, and the other point of measurement is over here, there's no correlation between the measurements at the 2 points if they're done simultaneously. The outcome of the measurement here does not affect the outcome of the measurement here. Well, in topological materials, they have these kind of edge states, and you have to do a little bit of work to change something. So the basic point is if I took a topological material and managed to break it into half, into 2 pieces, eventually when it was broken, I would have the new topological edge states would have opened up across the boundary where I cut it. And in some sense, there's a structure, it's not exactly the full entanglement, but there's basically structures which go across the material, and the topological edge states can be viewed as the termination of entanglement across the system. So topologically trivial states of matter can be assembled just by bringing a load of atoms together and stacking them in contact, and nothing else changed. But if I have a non-trivial state of matter, which is not just, this would be something like a rare earth solid or a van der Waals solid, I've kind of brought these things together and nothing particularly happened. The topological, if the state was topological, along the way, at some definite point as I brought them together, something would have had to change. And the orbitals, the electronic, which are little boxes that contain the electrons centered on the atom, will get rearranged at some point at a particular transition point to form chemical bonds or something. And basically, I think missing here, the electrons are basically liberated from their atomic, some of the atomic orbitals, and rebound in a new way in a state with non-trivial entanglement. So the earliest example was the spin chain, which was at least cited for my prize. So basically, in heavier atoms, electrons in a group of atomic orbitals can be locked together to form larger parallel spins. And the spin of an individual electron is set to be spin 1/2 conventionally. And in a rare earth magnet, where you want to line up parallel to each other, I start filling the f orbital or the d orbital. The electrons first go into the orbitals parallel to each other, because that reduces their Coulomb repulsion. And then once they've filled all the orbitals in that shell with upspin, I start to go backwards and put second ones in, and eventually I've removed the magnetism. So a large spin magnet can be viewed as lots of individual spin 1/2s added together. And the formal spin is then S, which is 2s, the number of such spins which are parallel times 1/2. So if there's the number of elementary spins that make up a large spin is going to be an integer number, and it's going to be even or odd, and the spin here will be half integer or integer depending on whether there's an even or odd number. So around about 1981, I discovered that a spin 1 chain of spins could have a novel state which is now understood to be the simplest of the topological states. The original picture that people had conventionally at the time for this was essentially bringing a load of magnetic atoms together without entanglement, so just stacking them together in such a way that their spins in this particular model were antiferromagnetic, which meant that neighboring spins wanted to be pointing in the opposite direction. So this is a spin 1 up, spin 1 down, spin 1 up, etc. But there's no basic entanglement. This is just stacked together, and this was a conventional picture of magnetism. And it worked pretty well for higher dimensional systems, three and 2-dimensional systems. But in 1 dimension, I discovered that the actual state of the spin 1 chain was something where the spin 1 splits up into its 2 component spin 1/2s, and then they form this maximally entangled state with 1/2 of the neighbors. So the interesting feature here was that these microscopic spins kind of break up and recombine, and you get left with, at the end of the chain, 1 spare half integer spin. And that was quite unexpected at the time. And so the new state can only occur if the spin is integer, because if there has to be an even number of microscopic spins on each atom for it to split into 2 halves. So this works for spin 1, but not spin 1/2. And so it depends on whether this number 2s, which is a whole number, is even or odd. And at that time, there was a conventional wisdom about magnetism was that the quantumness of a magnet was just a continuous function of 1/s treated as a real number, with no qualitative changes as the spin varies. And so for large spin, you could treat the thing semi-classically, basically as a a top which was pointing in some direction, and then as the spin was decreased, 1 over s increases, you take into account a little bit of 0-point motion fluctuation around the direction of the axis. But the new state was predicted to have an energy gap separating the ground state and the excited state when spin was 1, but not spin 1/2. So there were apparently very convincing arguments for the conventional wisdom at that time. So usually when there's some, conventional wisdom is usually correct. And people have convinced themselves of it because they're pretty good arguments for it. But sometimes there's some flaws in the argument. So the semi-classical analysis for large S worked very well, where the spins were pointing in some direction, but doing slight quantum motion around that direction. But there was, and this actually works in higher dimensions, but not in 2D, not in 1D. But there was also a mathematically exact solution of the spin 1/2, the most quantum case, which was discovered quite remarkably by Hans Bethe in 1931 when he was a graduate student. And that case was a very complicated mathematics, which no one really properly understood at the time, but you could work out and see what exactly its energy spectrum was, and this one had no energy gap. And quite coincidentally, it looked almost the same as what you would predict from the semi-classical spin wave theory. So there was a apparently correct exact mathematical statement about this strongly quantum limit of spin 1/2, which seemed to confirm to people that the spin wave theory from the semi-classical limit was consistent all the way down for all values of spin. And of course, I found this, of course, not because I was working on magnetism. And this is an example of how one actually can get new results. I was working on something completely different. And then I realized that would have some application to getting a better understanding of this model that Bethe had solved, the spin 1/2 model, and it did. And of course, having got a better understanding of the Bethe's model, it immediately suggested the generalization to spin 1, spin 1/2, spin 1 is best, to work upwards from the bottom. And the result that the conventional wisdom was wrong was completely inescapable from this new, different viewpoint I was looking at it from. So this shows you that if you can put knowledge of something that you know about to a different problem, you can often make a kind of contribution that the people working on that problem didn't make, because any new perspective is either going to give you new ways to confirm the existing answers or possibly occasionally give you a new way to see what's really going on. So this actually was turned out to be a very controversial thing, and people seem to be very committed to the old conventional wisdom. And in fact, my paper was rejected by 3 journals in a row, and even at a conference somewhere in Denmark, a senior person stood up and said, "This is complete nonsense." It was really quite a kind of violent reaction to this for some reason, which I didn't quite understand. But in science, arguments can be settled. There's actually a correct answer to distinguish between 2 different propositions about something. And material science has been the key in most of these new developments. Someone eventually got together to make a spin 1 chain because there actually hadn't been any experimental evidence about what a spin 1 chain would do or not. But because of material science and organics and things, people made a chain of nickel atoms embedded in an organic molecule. And eventually neutron scattering confirmed the energy gap. And the controversy actually was a very powerful motivation to lots of things. Very new experimental techniques got developed, and new theoretical tools. People didn't like to accept it, so they called it a conjecture rather than a prediction. But a lot of people wanted to weigh in on this, and in fact, things like the density matrix renormalization group, which has become a very important tool in theoretical studies, was actually developed one of the ways to test this idea. So it shows that controversy in science is actually extremely important. It gives rise to new things happening, and it's always very good for innovation. So, okay. So the meme of this is that, like a chain of people, you might say hands come in pairs, but unless there's been some kind of accident or something. But here, if people form a human chain, you'll find individual hands at either end of it. Okay. Okay. So anyway, there was this picture of my state, which is actually due to Affleck, Kennedy, and Lieb got stuck on the certificate you get. You get a kind of watercolor, which interpretation of your work on the Nobel thing. So the other important. Most important thing was, of course, in 1980 was the quantum Hall effect discovery by von Klitzing, which was also an accident because he did the experiment in a way that would actually forced him to see that there was something strange going on. He got a voltage on his voltmeter which was accurate to 5 or 6 significant figures. Every time he did the experiment, when he switched the magnetic field on, he switched the magnetic field on this device with a fixed current, and he always got the same value. Other people have done the same experiment where they put the thing in the field at first, in a fixed field, and switch the current on. You never get the same answer for the current that way. So it's kind of accidental that he found this remarkable result that the electrical conductor, the whole conductance of this was an integer times fundamental constant. So of course this has democratized the system of units. Before we had to go to Paris, you had to check your market traders' weights could only be in principle checked against a lump of platinum in Paris, which Napoleon had created, while now anyone can build a kilogram by the Kibble balance based on this. So the topological nature of the quantum Hall took some time to become clear, but basically electrons go around in little circles in a magnetic field, but along the edge, if these little circular orbits hit the edge, they kind of go around in a skipping orbit, and you see there's this characteristic feature of one-way transport at the edge state, which topological things have. So the integer quantum Hall effect was soon followed by an even bigger puzzle, the fractional quantum Hall effect, and at Bell Labs again. And since only 3 people can get the Nobel Prize, the theorist Bob Laughlin, who came up with the explanation, and the people who did the measurements, but not the person who built the device, got it. You can see from this the forgiving nature of topological states. I mean, this would not, if you submitted this as your work, you wouldn't get a job at Taiwan Semiconductor making their chips. But because of the fact that topology is stable against a certain amount of dirt and stuff, this device showed the effect. So the key thing was the Laughlin state, and this is, in my view, one of the most remarkable things that were found. The Laughlin state has a very simple form. He discovered it accidentally by doing numerical calculations on a 3-particle system. And the key thing about it is that in this state, instead of electrons occupying individual orbitals, as they do in a regular condensed matter system, you fill the electrons, you put 1 electron of each spin up or down in the orbitals as you go up in energy. Here, all the orbitals in the level have the same energy. And the electron doesn't fill just 1 orbital. When you put it in, it actually fills 3 orbitals. It creates a void around it, which is occupied by 3 orbitals. And it's this state that is completely different from the standard Slater determinant states which are familiar here. And of course, if every electron uses up 3 orbitals, then the number of all the orbitals will be used up when the number of electrons is 1/3 of the total number of orbitals, which is the filling of the Landau level. So when I have this thing, if I remove 1 electron from this state, I leave 3 empty orbitals behind. And the Coulomb energy is lowered by this thing splitting up into 3 individual orbitals, and these things are the famous quasi-particles that obey fractional statistics and carry 1/3 of a charge. But this is still not enough to give you the quantum, the topology needed for quantum computing. This stuff showed all this stuff has been verified, but the most interesting thing is a more general version of the quantum Hall effect called non-abelian, which is where instead of one particle occupying 3 orbitals, we have a pair of particles occupying 4 orbitals. And when I pull out this pair, instead of splitting up into 4 individual orbitals, each carrying 1/2 of a missing charge, it splits up into 8 orbitals carrying 8 half orbitals carrying 1/4 of a charge. So this is a very strange thing. The orbital has fractionalized into 2 half orbitals. These are called Majorana zeromers. This is something which is very difficult to get your head around. But when you take an individual orbital and you split it, you can only make have an individual orbital created locally or emptied locally. If you split it into 2 half orbitals, there's some entanglement pattern between the 2 halves, which tells the history of how this was made. But it's totally invisible when the orbitals are very far away from each other. And that's the basic idea for the topological qubit. The elementary qubit, which carries 1 unit of information, is made by initially 4 of these things, and the information is stored in how they were created. But if I look at this thing, I can't tell I only see the pattern of the 4 quasi-particles here, the charge minus 1/4 objects, and I can't see the difference between this and this. And then by braiding or moving these things around, I can stir up this pattern. And the entanglement pattern, as it varies around, corresponds to different positions on the Bloch sphere of the qubit. And this is the idea is that the environment cannot measure the quantity here. So this thing is at least on paper, is protected from the environment. Okay, let's go through this. So this half orbital is actually something called the Majorana zero mode, and it's quite strange. But basically, if I take an orbital, which if a qubit is, if I think of a system here, I can either have the orbital filled or empty. After I pull it apart, I can't tell whether the system was empty or filled before I pulled it apart. So that's the information of empty or filled has been hidden in the environment, and to get it back again, I have to push these things back together, and then I can measure whether they're filled or empty. So if I pull them apart one way, move them around, and join them back at the other way, I have this quantum information processing. So the magic of this is that as a pure topological thing, the information is completely hidden. But if you actually do this thing, look at it carefully, the information is only hidden when the distance between these fractional 1/4 things is very far apart on some length scale. There's always some exponential kind of tunneling length scale. And here, this is a smaller system, and you can see that these are the 2 states of this qubit, up and down, say. And you can look, if you see there's a little bit of kind of wiggles, interference fringe patterns, the basic places where the charge is located looks the same in both cases. But as I pull these things far apart, eventually there's an exponential decay length, and the wiggles will get exponentially smaller and smaller and become formally invisible when the things are separated on large compared to this microscopic scale. So that's the thing. So I'm running out of time, but Microsoft has spent a lot of time on trying to make a qubit this way. It turned out you can make these Majorana modes. You don't need the quantum Hall effect to get them. There are other ways to do it with superconductors. And basically, the Majorana says I can split an electron creation operator like a complex number into a real part and an imaginary part, and the 2 halves are like the Majorana's thing. So in the example, which was the Microsoft thing, which is based on the Kitaev chain, you put the thing in a superconductor, and essentially the electron orbitals split up, but then they rejoin in a certain way. They rejoin to form simple orbitals with their neighbors, but in such a way that you leave half an orbital at one side of the system and half of the orbital at the other side of the system, which is exactly a much more profound and disturbing kind of version of the fractionalization of spin 1 into 2 spin halves. This is a fractionalization of an orbital into 2 half orbitals. So basically, if I put an electron into the system and take it out here, I've got all kinds of paradoxes which are there. Okay, so it turns out that you actually don't need a magnetic field to get a quantum Hall effect. This is the latest developments. Way back, I came up with a toy model, which turned out to be quite influential, that you can get a quantum Hall effect just from magnetism. And it turned out to be in a model based what we now call graphene, with some second neighbor hopping. And if I take this toy model and tune the band parameters, you can actually make the conduction band very, very narrow, almost as narrow like a Landau level. And about 10 years ago, people did numerical simulations on this, and they found a fractional quantum Hall effect occurred in a narrow, a quasi-flat band of this model. And that was a kind of theoretically interesting thing for a long time, but it's taken off last year when the fractional quantum Hall effect in flat bands, narrow bands, was discovered in what is now twisted bilayer graphene, 2 sheets of graphene on top of each other to form a moire pattern. This gives you a kind of basic lattice structure much larger than the original microscopic one of the graphene. And by finally tuning these things, you can get very flat bands. And initially, superconductivity was found in this, a remarkable thing. But last year, or year before last now, I guess the quantum Hall effect was found here, fractional quantum Hall effect. So the last thing is that, so this has given a lot of new hope to a new platform for maybe we'll actually find a material realization of the topological qubit. But as an aside, people have actually done other things with simulating the topological qubits with trapped ions by basically taking synthetic systems where you have trapped ions which have a very long lifetime for coherence, and basically doing formally kind of building a quantum state by bringing ion number 33 and making it have a little gate to couple to 201 or whatever, and then moving them around a bit like at the dry cleaners when the suit can be on some kind of stack and in the way back in the store, and they can bring it out on a racetrack to the customer. So you bring these trapped ions and bring them there, and you can simulate things, and quite remarkably, some very interesting stuff has recently happened that way. So I guess I'm out of time. I would say that the topological qubit is a beautiful dream. It's been very inspiring. It hasn't been achieved yet in a concrete way. And I guess I'm not going to advise people to put all their money in a company trying to make topological qubits yet, but I believe it will occur at some point, and we'll find out. But maybe the future of topological qubits is as virtual as better error correction codes than actual practice. We'll find out. Okay, so let's just see. Out of this, I want to finish with a motivational message. A lot of the work I described was actually accidental. At least the 2 things of my work I mentioned were not deliberate. They kind of accidental things. Laughlin's state was actually accidental. Von Klitzing's measurement discovery was accidental. So the thing is that the best discoveries that are waiting to be made are discoveries that no one actually dreams are there to be made. Because there's really plenty of smart people around there, right? So it's like treasure, right? If they had a sniff that there was a treasure buried on a certain beach, they'd have been out there digging till they found it, right? So but I think this is an example that actually anyone who does basic research of some kind has got and who has got the time to look around a bit, and if they see something unusual along the path they're traveling, to investigate it. Everyone has a tiny, tiny chance of actually finding one of these discoveries, which will, be so important it might eventually get a Nobel Prize or something. But the crucial thing is to have the preparation, to have the time, first of all, not to be completely focused in going one direction, but if something interesting or different shows up, to actually investigate it a bit, and again to prepare it. And if it's something controversial, you may have to fight for it, as I had to do in some way. And of course, these luck and commitment, etc., are exactly the same thing you hear at business school commencement addresses. So you need a lot of luck to make these discoveries, and you need the preparation and the passion to push it forward. Thank you.
Thank you, Prof Haldane. Let us now invite Prof Yang Po to moderate this session.
Okay, can you hear me? Okay, thank you very much, Professor Haldane, for this wonderful talk and for sharing with us your fascinating journey through quantum mechanics, entanglement, and topology, and also to show us what these interesting concepts could do in the future for the years to come. So without further ado, now we are open to the floor. So if you have any questions, we have the mics over there, please. Okay, so maybe start with the first question. Okay, so you mentioned about the topological quantum computers, and of course now Google and IBM also have these superconducting qubits. Mm-hmm. So in terms of the quantum computation perspective, what are the main challenges, mainly on the material designs and engineering, or the fundamental aspects of quantum computation?
I mean, the real question in quantum computing, I suppose, is assuming we get it, what you can actually do with it, right? Uh-huh. Besides breaking credit card codes and things, right? Okay. So it's still open what we'll actually get out of the quantum computers when they arrive, assuming they arrive. The current, it's been quite surprising how much better the quality of the qubits mm-hmm. Has got better and better, and with all the people working on it. Initially, people thought quantum computing must be, crazy and it's not going to happen, but we'll find out. Now we're IBM and people talking about several hundreds of qubits, right? And it's very interesting, this development of simulating uh-huh. matter by synthetic matter, by just bringing qubits together, which are not physically located, but bringing them together and interacting a little bit, and basically having a quantum circuit mm-hmm. design. And it's quite so. In some sense, it's great that some validation of the topological qubit seems to be occurring using noisy intermediate scale right. qubits. Of course, the whole point of the qubit would be that it would be better than these guys. But if it doesn't happen, possibly, as I said, it may well be that these ideas will have importance for quantum error code, quantum error correction or something.
Okay. Yes, we have a question over there.
Hi. I was curious about the Pauli exclusion pairing, specifically for other D-block elements, say something that has like a crystal field splitting energy. So that complicates the pairing a little bit. If your crystal field splitting energy is prohibitive, then you're not going to, and with respect to the spin pairing energy, that determines whether you're in the high spin configuration or the low spin yeah. configuration, and dictates the oxidation state. So I guess my question is whether or not the state that you're in, or how it influences the qubit, and if it changes the strength of any kind of entanglement or some other characteristic thereof.
Well, the issue there was how you could get these states which are not the neutral picture of magnetism was the spins all lined up parallel, and ferromagnet, they're all pointing the same way, and it can pick up a paper clip. An antiferromagnet, they're alternatively up and down, and there's a kind of broken symmetry state there. The issue was that this is the first example of a spin liquid, and actually there are a lot more spin liquids. A spin liquid means you actually got a state with no broken symmetry, and in this case, an energy gap protecting it. And a number of spin liquids in 2 dimensions have emerged over the years, so these are different from the standard magnetic states with order. If you have too much crystal field splitting, eventually you will go to a more, you will get to a different state. But these were kind of unexpected ways of making quantum states of magnets. And basically, it's in the example here, it's because in one dimension, the quantum fluctuations, it was known that eventually the spins will fluctuate to explore all directions, while in an ordered magnet, they're just oscillating around a kind of broken symmetry, a particular direction. And basically, the difference between an integer and a half-integer spin is sort of related to the fact if I manage to rotate a spin, completely around the circle, I pick up a -1 sign if it's a half-integer spin. So this was actually a quantum interference effect due to the spins eventually being able to travel, to point over all directions as a function of quantum fluctuations. Yeah.
Cool, thank you.
Yeah. Okay, yes.
Hello, Professor Duncan. Thanks a lot for the talk. My question is regarding how or what are the alternatives of materials to build this kind of topological quantum computers? I know these effects can be seen in 2-dimensional electron gases, but are there other alternatives to build these systems?
The basic thing was, the initial one is this Majorana zero modes, and people have, there was a whole lot of excitement in Delft in Holland around 2016, and where people thought they'd seen the Majorana modes. It turned out maybe they hadn't, because there wasn't basically they saw something called a 0.0 bias anomaly, and they tried to rule out all other things it could be. So it wasn't a very positive identification. It was identification because it couldn't be anything else, and it turned out that was not correct. You could make so it turns out the Majorana zero mode, which I kind of described, where essentially an orbital has split up into 2 half orbitals, doesn't give you universal quantum computing, but if you could a more complicated state which doesn't have so far any kind of guessed at physical realization. There is a belief that the one I showed does have a physical realization in half-filled second Landau level. Is actually if you split the orbital up into 3 pieces, not 2 pieces, you actually the kind of entanglement you get from that will give you on paper all possible quantum gates needed for computing. But it's a bit like it's a bit like fusion, right? On paper, fusion works. This stuff works fantastic on paper. Now it actually seems to be working in simulation with NISQ qubits, but it remains to be seen whether we can actually come up with the material platform. But certainly there's a huge amount of work on this, and all the proposals to the funding agencies, of course, are justifying this because this may lead to the topological quantum computing, which would really, I say, would really solve a large part of this problem of hiding the information from the environment. If you've got this, if the information is sequestered when the objects are far apart, the only place you can lose the information is you've got to put the information in. These objects have to be combined to be a regular orbital, which you can then see whether it's empty or filled. So to put the information in, you have to worry about losing the information when separating it, and to bring the information, make it readable again, you have to bring them back together. But if this works, then you can do many more. You're not limited by exponential fall off by how much you can do processing it while they're separated. You only have danger at the read in and read out stage.
Thank you.
I actually have a follow-up question. So a lot of your research focuses on low-dimensional systems, like the 1D systems, Lagrange liquid or spin chain, or 2D fractional quantum Hall. Can you tell us a little bit about why lower-dimensional systems are more interesting comparing to?
Well, the quantum effects are stronger so these are quite remarkable systems. I say the fractional quantum Hall systems are kind of strange, right? It's because you have some kind of, first of all, you've lost the kind of kinetic energy of the electrons. Usually when you put electrons in something, you've got a set of one particle orbitals, and you fill them up from the bottom upwards, and then you either fill a band completely or have a Fermi energy when you stop filling it. The orbitals are kind of attached to the underlying lattice, right? Here, once the kinetic energy becomes negligible, the orbital, in these cases, the orbitals themselves are detached from the lattice. And essentially, they actually are, because they have this topological character, they're fundamentally non-orthogonal to each other, and they're more fuzzy. And they attach themselves to the electron rather than there's nothing else for them to attach to. In the original case, in Landau levels, the orbitals were detached from the lattice by the magnetic field. There was one orbital for every quantum of magnetic field. In these new systems, where there's no magnetic field, you still have the orbitals are kind of detached from the lattice, and they're free to move. And so an electron can occupy or keep to itself more than one orbital, and that means each electron is kind of surrounded by a little bubble, and that keeps it isolated from the other electrons, and it's the short-range interactions that drive this. So the Pauli principle is not responsible for this structure anymore. It's actually the electron-electron repulsion which dominates when the kinetic energy of the band has gone. It's a rather remarkable state. But so it can't be treated by the usual band structure methods that we use for ab initio calculations of all kinds of materials.
Right. Unfortunately, we're really running out of time. So if you have more questions, you can always ask Professor Duncan Haldane during the tea session. So let's thank Professor Haldane again.